This video is about finding the probability of independent and dependent events. It's lesson 33 in the book on pages 204 through 210. Independent events are events in which the outcome of one has no effect on the probability of another event. Now, that would be like the probability of flipping heads twice on a coin. The result of flipping the coin once actually has no effect on flipping the coin the second time. So those two are independent events. To find the probability of two independent events, you simply multiply the probabilities of the two events. For example, the probability of spinning a 3 on the spinner and flipping heads on the coin would be the probability of spinning 3 times the probability of flipping heads. Now, whatever we spin here has no effect on the result of the flipped coin and vice versa, so these are independent events. The probability of spinning a 3 here would be 1 out of 5, and the probability of flipping heads on the coin would be 1 out of 2. So to find the probability of 3 and heads happening, we would multiply our probabilities and get 1 over 10. 1 times 1 is 1, 5 times 2 is 10. Here's another example of independent events. What would be the probability of spinning a 5 and then spinning a 1? Now, the first spin has no effect on the second spin, so that makes them independent events. And in order to find the probability of both of those things happening, we would find the probability of spinning a 5, which is 1 out of 5, and then multiply it by the probability of spinning a 1, which is also 1 out of 5. 1 times 1 is 1. 5 times 5 is 25. So the probability of spinning a 5 and then a 1 would be 1 out of 25. Dependent events are events in which the outcome of one event does affect the probability of the other event. Now, to find the probability of two dependent events, it's very similar to finding the probability of independent events. You simply multiply their probabilities. However, the second event is affected by the first, so your probability in the second event is going to be calculated a little differently. An example of this would be if you had a bag of marbles, and you drew one out, and then you didn't put it back, and you drew another one. The probability of that second marble being a certain color or having a certain number on it would be affected by what you took out of the bag the first time you drew a marble. So those two are dependent events. Independent events, here's some definitions, just some general stuff. The outcome of the first event does not affect the second, so you just multiply their probabilities. Dependent events, the outcome of the first does affect the second. So you still multiply their probabilities, but B is calculated under new conditions. Alright, so this slide is an example. It needs to be in your notes, and we just want to identify whether these events are independent or dependent. Example A says rolling a 6 on one number cube and a 4 on another number cube. Now, since rolling the first number cube has no effect on what we roll on the second number cube, these two events are independent. The first one will not affect the second one in any way. Part B says rolling a 6 on a number cube and then a 4 on the same number cube. Now, this is different because we're using the same number cube both times. But again, what we roll on the number cube the first time does not affect what we roll on the number cube the second time. So these events are also independent. Example C says drawing a red marble from the bag, keeping it out of the bag, and then drawing a blue marble. Now, when we draw the red marble from the bag and we keep it out of the bag, that changes the total number of marbles in the bag, which therefore changes the probability of drawing a blue marble. Since taking the first marble out and keeping it affects the probability of what the second marble will be, those two events are dependent. In part D, drawing a red marble from a bag, putting it back in the bag, and then drawing a blue marble. When we drew the red marble from the bag, that changed how many marbles total were in the bag. But when we put it back, it replaced the missing marble, and so it didn't actually have any effect on whether or not that second marble was blue. So since we put the marble back, the first marble did not have any effect on the second marble, making these two events independent. Here we're going to use a tree diagram to calculate our probability. It says you flip a coin 2 times. Make a tree diagram showing all possible outcomes. What is the probability of the coin landing on heads both times? Okay, so we're going to flip a coin twice. Now, the first time we flip the coin, it could either be heads or it could be tails. This needs to be in your notebook, by the way. Now, if the first one is heads, we're going to flip again, and the outcome could either be heads or it could be tails. If we flip tails, of course we're going to flip again, and the outcome could either be heads or tails. So there's our tree diagram. That shows all the possible outcomes. Heads, 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 tails, tails, heads, and tails, tails. Then we also want to know what is the probability of the coin landing on heads both times. Well, the only possibility in our tree diagram where the coin lands on heads both times is right here, heads and then heads. So that's one favorable outcome. Out of the total number of possible outcomes, we have heads, 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 tails, tails, heads, and tails, tails. So that's 4. So the probability of the coin landing on heads both times would be 1/4, or we could write it as 0.25 or as 25%. Now we're going to calculate the probability of dependent events. This again is an example and it needs to be in your book. Natalia has 2 squares and 3 circles in a bag. First we want to find the probability of drawing a circle, keeping it, and then drawing another circle. So first we need to find the probability of drawing a circle the first time. Now we know that there are 3 circles in the bag out of a total of 5 shapes because we have 2 squares and 3 circles. So the probability of drawing a circle the first time is 3 out of 5. Then we need to find the probability of drawing another circle after the first one is already taken. If we drew a circle the first time, there are only 2 circles left in the bag. Now there were 5 shapes in the bag, but since we took one out, now we only have 4 shapes in the bag. So the probability of drawing the circle the second time would be 2 out of 4. To find the probability of both of these things happening, notice this and, we need to multiply these two probabilities. 3 times 2 is 6, 5 times 4 is 20, and when we reduce that by dividing both the top and the bottom by 2, we get 3 out of 10. So the probability of drawing a circle, keeping it, and drawing another circle is 3 out of 10, 4.3 or 30%. Here's another example that needs to be in your notebook. Again, we have this 2 squares and 3 circles in the bag. We need to find the probability of drawing a square, keeping it, and then drawing a circle. So first we need to find the probability of drawing a square. So probability of a square. Now there are 2 squares in the bag out of a total of 5 possible shapes. Then we need to find the probability of drawing a circle, given that we've already drawn a square out of the bag. Now, the probability of the second event, drawing a circle, there are 3 circles left in the bag. Since we've already taken a square out, there are only 4 possible shapes in the bag. So the probability of drawing a circle that second time would be 3 out of 4. To find the probability of both of these things happening, again, notice the and, we would have to multiply those probabilities. So we have 2 times 3, which is 6, and then 5 times 4, which is 20. And again, when we simplify this, we get 3 out of 10. Alright, now odds are a little bit different than probability. The odds of an event happening is a ratio expressing the likelihood of an event, so kind of like probability. However, that assumes that all outcomes are equally likely and that there are m favorable outcomes and n unfavorable outcomes. Now the difference here is that probability compares the number of favorable outcomes to the total number of outcomes. Odds compare the favorable outcomes to the unfavorable outcomes. The odds for an event are m to n, favorable to unfavorable, and the odds against the event are n to m, or unfavorable to favorable. In this example, which needs to be in your notebook, we're going to calculate odds. A bag contains 6 red marbles, 2 yellow, and 1 blue. First, we need to know what are the odds of drawing a red marble. Now, odds means we're comparing favorable to unfavorable, and in this case, our favorable event is drawing a red marble. So how many red marbles are there? Well, there are 6. And we need to compare that to the number of unfavorable outcomes, so not drawing a red. Since we have 2 yellow, which are not red, and 1 blue, which are not red, there are 3 unfavorable outcomes. So the odds of drawing a red marble are 6 to 3. Now, this, just like a fraction, can be simplified. Both 6 and 3 are divisible by 3. So the odds of drawing a red marble are 2 to 1. Again, the difference is we're comparing favorable to unfavorable, not favorable to total. In example B, we need to know what are the odds against drawing a blue marble. Now, we want to know what are the unfavorable outcomes compared to the favorable one. Now, the favorable outcomes are drawing a blue marble. So first we need to find the unfavorable outcomes because it says the odds against. Only 1 marble is blue, but 6 are red and 2 are yellow, which makes a total of 8 unfavorable outcomes. And we need to compare that to the number of favorable outcomes, and since blue has only 1 marble, our odds are 8 to 1. Now we're going to solve a multi-step problem involving probability. This needs to be in your notebook. Isaac has 6 blue and 4 white shirts in his closet. There are also 2 pair of navy pants and 3 pair of khaki pants in his closet. What is the probability that Isaac will choose khaki pants and a white shirt? Now this means we need to find the probability that he's going to choose khaki pants and multiply it by the probability that he will choose a white shirt. Since he has 3 pairs of khaki pants in his closet, out of a total of 5 pairs of pants, 3 khaki and 2 navy, the probability that he'll choose khaki pants is 3 out of 5. The probability that he'll choose a white shirt, since there are 4 white shirts, out of a total of 10 shirts, 6 blue and 4 white, the probability is 4/10. And to find the probability that both of these will happen, we simply multiply them. 3 times 4 is 12. 5 times 10 is 50. We simplify that, we can get 6 out of 25. And finally, after the pants and shirt are worn, they are put in the laundry hamper. What is the probability that he will choose khaki pants and a white shirt from the closet to wear the next day? Now this means 1 pair of khaki pants and 1 white shirt is already gone. And we want to figure out the probability that that will happen again. So now the probability that he will choose khaki pants is only 2 out of 4. He used to have 3 pair, but 1's in the hamper. And he used to have 5 pairs of pants, but that same pair again is in the hamper. We're going to multiply that by the probability that he'll choose a white shirt the second day. He used to have 4 white shirts, but since 1's in the hamper, he only has 3. He used to have a total of 10 shirts in his closet, but since 1's in the hamper, now he only has 9. And when we multiply these probabilities, 2 times 3 is 6, 4 times 9 is 36, and when we reduce, we get 1 out of 6.